So a lot of you have been asking for extra examples. So in this particular slide deck, I will just go over a number of extra examples for DC circuits. And in particular, I'm just gonna focus on these 4 resistor networks and a few current mirrors, which is what you really need to know in terms of DC analysis. What you will see when we look at the amplifier analysis is that we will actually use the same 4 resistor topology to bias our MOS amplifiers, and it will be kind of the building block that we will use for amplifiers. So it's basically the circuit that you really need to know how to analyze. Okay, so let's look at this particular example where they actually give us the value of the current flowing through the MOS transistor. They also give us Kn and V threshold, and they ask us to choose to find what VDS should be at first. Well, since we know what ID is, we know what RD is, and we know what RS is, we know that basically the voltage VD, which is this one, just be the voltage here, which is 15, minus the voltage drop across here. So it's going to be VDD minus ID times RD, which is just equal to 15 minus 0.5, which was given to us, times 10. So remember, 0.5 milli times 10 kilo. The milli cancels out the kilo, so it's just times 10. So this is just going to give us 0.5 times 10 is 5. 15 minus 5 is just 10 volts. For Vs, we have 0 volts here. And we know that the voltage up here will actually be Vs, which is ID times Rs bigger. So it's going to be 0 plus ID times Rs. So that's going to give us 0 plus, well, ID is 0.5 and Rs is 10. So it's going to give us 5 volts. So now we know that VDS is equal to 5 volts. Okay, so now we know VDS. And so that's basically all it's asking us. Let's see what it asks us on the next slide. Okay, so let me go to the next slide. All right, so it asks us to find VDS. Well, we just found it. It was 5 volts. Here, I just go through the same math that I went in the previous slide. So now let's look at our next question. So now it's asking us to find the VGS required to get the correct current. Now, what is the VGS that we need to be in saturation or to get this current? Well, we need ID to be equal to K over 2 times VGS minus V threshold squared. So we need that to be 0.5. We got our K, which is equal to 1. Our threshold, which is equal to 1. So we have that VGS minus 1 has to be equal to 1. So we can take the square root of both sides. So we're going to get that VGS has to be equal to 2 volts. And we know that Vs is equal to 5 volts. So that means that Vg here has to be 7 volts. All right, so now we can actually figure out what the resistances are that would get us 7 volts there. And of course, since there's 2 resistances, we can choose one however we want, and then the other one will follow from that. Okay, so let's continue on with this. Yeah, so we chose it for saturation. Okay, so let's assume that we choose RG1 to be 8 mega ohms. What does RG2 have to be? Well, we need 15 volts minus 8 mega ohms I. So I'm going to call this I, to be equal to 7 volts. And we also need 0 plus Rg2 I to be equal to 7 volts. So we can actually subtract these two equations. And then that's going to give us that 15 minus, so if we subtract those two equations, actually we can solve this equation for I. So here we have 7, we subtract 15 from 7, that will give us 8 divided by 8, that will give us negative 8 divided by 8, and that's going to give us that I has to be equal to 1 microamp. And so if I has to be 1 microamp, that times Rg2 has to be equal to 7, so that gives us that Rg2 has to be 7 microamp, 7 mega ohms. That's it. So now we know what Rg2 has to be to give us our value for the gate voltage. So as you can see, these circuits are very similar in terms of solving to standard KCL, KVL type circuits that you solved in circuits 1. All right, let's look at another example. So slide 8, okay. All right, so we need to figure out what IX is. So just as a reminder, whenever we have a current mirror, for this particular transistor, this would be kind of the one driving the whole circuit. And in particular, we know that the VD1 will actually be equal to VG1, which will automatically tell us that this circuit is in saturation. At this point, since we know that the circuit is in saturation, we know that basically ID will be equal to K over 2 VGS minus V threshold squared. Additionally, since VDS and VGS are the same, we can actually replace this with VDS1. So this is only for the first transistor. That's why I'm putting a 1 after it. I should probably put an ID1 here to denote that this is the current going through the first transistor. Okay, additionally, the voltage VD1 is actually equal to volt VDS1 because the source is grounded. And additionally, so we have 5 minus 3 kilo ohms, ID1. So now we can actually just plug this equation back into this equation and then solve for the quadratic equation like we did in the previous example. In particular, we have here that K is 2, V threshold is 1, and so we will get that ID1 will be equal to 5 minus 3 ID1 minus 1 squared, and that's going to give us 16 minus 24 ID1 minus or plus 9 ID1 squared. All right, when we move the ID1 to the other side, we're going to get negative 25, so we have to solve the quadratic, this following quadratic equation. So we have 16 minus 25 ID1 plus 9 ID1 squared. So we're going to have 25 divided by 18 plus minus, this ID1 is equal to the square root of 25 squared, which is 125. So 25 times 25. I think it's 1. No, it's actually a lot more. It's 525. So 5 times 25 is 125. Times 5 of that gives you 500. And then 25 times 5, that's 125, so 625. And then we have to subtract from that 4 times 9 times 16. Okay, so 4 times 9 times 16, and luckily I have my calculator here, so 25 times 25 minus 4 times 9 times 16 gives me 49. So actually this whole thing turns out to be 7, and then divided by 16. So we're gonna have that actually 18, sorry, ID1 is equal to 25 plus or minus 7 divided by 18, which is equal to, so 25 plus 7 gives me 32 over 18. Or it's going to be minus 7, which gives me 18 over 18. Now, if I have 32 over 18, the reason that it's not that is because 32 over 18 times 3, that will give me 32 over 18 times 3. It's going to give me 5.33. So basically, VD1 equals 5 minus 3 times 32 over 18. That's going to give me 5.33. I mean, negative 5.33. And that cannot be in saturation. So as a result, that means that it cannot be that one. So it's not this one. Now, if I have 18 over 18, then I have VD1 equals 5 minus 3 times 1, which will be equal to 2. So that one actually works, because if this is 2 volts, then VDS, which is equal to VGS, is greater than V threshold, and then we're in saturation. Cool. All right, so now we know that 1 milliamp flows through here. Now comes the interesting part. Well, as we said before, because 1 milliamp flows through here, that means that 1 milliamp has to flow through this one, because all of these are identical. And that also means that 1 milliamp has to flow through this one. Since 1 milliamp has to flow through this one and 1 milliamp has to flow through this one, that means that 2 milliamps has to flow through this one. So I've asked this question multiple times in an exam, and usually a lot of students get it wrong. In particular, a lot of them get to this, but they don't realize that if I keep connecting these circuits side by sides, the currents will just simply add. So just to give you another example, let's say that I were, to make this most interesting, add another identical transistor. Okay, so this should give me enough space to draw my other identical transistor. So let's say I connected another transistor here. And then there's another line here. This is going to be M4. It turns out 1 milliamp would also flow through here. So I would make this be 3 milliamps because now you have this current plus this current plus this current. So it doesn't matter how many transistors I keep drawing, they just keep adding the current so that now I get more and more current across this IX resistor. Of course, there's one caveat. If you put too many resistors in parallel, this voltage cannot drop below a certain value, otherwise you won't be in saturation anymore. So at this point we're still safe because if you look at it this closely, if we have 3 milliamps, the voltage here will be equal to 5 minus 3 times 0.5, which will give me minus 1.5, 3.5 volts. And since all these VGs are actually at 2 volts, then all of these will actually remain in saturation mode because VD for all of them will actually be, so this is 2 to VD4, will be 3.5, which is greater than 2 volts, so we're good. So it's important that you understand this particular example. It's important that you know how to solve all of these 4 resistor networks. We're going to go over some more examples in class, hopefully one more right before the quiz. And yeah, so that's basically some extra examples that you can look into.